Do let me know when to start. If you feel that adequate number of students have joined, we can start.
Yeah, I think we can start and people will keep joining in between.
All right. So does the slide change?
Yes, yes.
Okay. Yeah. So good afternoon and welcome to the post-lunch session of the day one of NSM Computer Architecture Winter School 2021. In this lecture, I am going to discuss about VLIW lecture. During the day, you had lectures about instruction level parallelism and superscalar, and this is going to be further to those concepts that you learned in the morning. So this is going to be the agenda for this lecture. We'll begin with an introduction where we will see how performance matters, and then we will have some background about that we will have to set some context we will set for understanding VLIW. And before we get into VLIW, some of the we will refresh some of our concepts related to single core performance. And then we will see how VLIW takes that performance further. And within that, we will just quickly look at how it started, what was the motivation for going in for VLIW, then the core thing about the basics of the architecture, how it works, then some of the design ideas, not much going into detail, just superficial about how that design philosophy is. And we will then see what are the advantages that we get as well as the disadvantages that VLIW offers. We will see a few implementations of VLIW, how they are being put to in practice, and we will end up with a summary followed by Q&A. So let's begin with the first section, that is introduction. And I guess you would be typing in questions, but I won't be able to see them. So what I will do is maybe midway in between, I will just have a look at the questions, and you will also have a chance to ask the questions, and then we will have another round of questions at the end. So at any point in time, if you feel that you want to ask a question which can wait till the mid, maybe about 45 minutes in the session, then you can type it in. And if it's something that you're not understanding and would you like me to hold and explain that, I think you can speak out and then I will respond at that time. So let this be the protocol. All right, so we will begin with some graphs. Okay. So the whole purpose of what you studied in the morning and what we are studying now is the improvement in performance. And this graph on the right shows how it has increased over the scale on the x-axis is the years. So over the years, how it has improved. And what is the base that they have taken? They have taken one of the very iconic, or somebody's requesting to present or something. I think that was by mistake. Mr. Sahib Panda, you can lower your request. I think I can't see it fully what it says, but possibly it is saying requesting to present or something. I don't know. Okay, requesting.
Sorry, it was by mistake.
Okay, okay. All right. So that's okay. That's okay. Such things do happen on online ways of communication. Don't worry. All right. So I was saying that this on the x-axis are the years and on the y-axis is the relative performance. At the origin of this graphs is a computer called as VAX 11780. So this was at that time there was a company by name Digital Equipment Corporation that was one of the iconic companies. You can see that IBM at that time was the top company, and DEC was Digital Equipment Corporation was maybe you can say number two. which these computers were very much popular in use. One of the examples that I can give you is when the passenger reservation system of Indian Railway started. The first two computers that were installed at PRS VT Bombay, where this VAC system may not be 11780, but one of those family members. And two of such systems were installed that were handling the entire load of reservation system at that time. So that is being used as the base. And as you can see, initially, you can say the per year growth rate in terms of performance was something like 25% in year. So like if you year on year, the performance would increase 25 times. So like 100, 125, then 25% of 125, uh, uh, and then add to that. Like this, it kept on growing. Subsequently, in 1986 onwards, there was even a really further jump. If you can see there, 52%. So 100 would become 150, then 150 plus 75 would become 225, and then 225 plus half of that. That's the rate at which it was growing. And those things that you see there, those are the systems. Like IBM has got, there was a RISC system, RS6000. HP came out with a PA RISC system. So Alpha was again from DEC. So like this, these systems kept coming in. And as I have mentioned here, the architects of these systems, like they have strived for improvement in performance. That has been their goal. So over a period of time, they just wanted a new system to come in. Why would somebody buy a new system? Only if it gives better performance. Okay. So that's what has been the goal. And one of the biggest contributor to this is Moore's law. All of you know that the transistor density increases, doubles. It becomes doubles every 18 months. And so that is one aspect that has definitely helped. But that's not the only aspect that has helped in improving the performance. And there are certain features which we shall describe. Some of them have been described in the morning, like pipelining, out of order execution, branch prediction. So these features have led to increase in a metric that is used to measure the performance of uh, a CPU, which is called as instructions per cycle, IPC. I might have heard about reverse of that, which is cycles per instruction. So it's the same thing. So instruction per cycle means how many instructions can you execute in one cycle. So typically the older processors would have like one instruction per cycle. That was also good. For a pipeline processor, it used to be one instruction per cycle. And prior to that, for non-pipelined, it used to be maybe 1/4 instruction per cycle or something like that. However, as I have mentioned here that in successive members of a processor family, so that's one part. Like many of you would have heard about this, what we call as x86 architecture. Okay. So now it began with 8086, then came 286, 386, 486, Pentium 2. So these are the successive members of one processor family because the codes are backward compatible. Any code written for 80386 is guaranteed to run on other newer processor, not the other way. That is a code written for, let's say, Pentium will not run on 386, but the reverse will be true. So like you have a processor family, like because that's the same company that is developing those successive generations, successive members of a processor family. Similarly, you can have across the family also, like IBM makes Power, a range of processors, or Freescale makes Power PC range of processors, or AMD, now they have naming it, but the AMD also makes it x86, just like Intel does. So there are families of processors and there are members in a family. And as point, the simple point being made is that over a period of time, as year progresses, the newer members that come, the newer processors that come, they are having some better features. And of course, they are definitely following the Moore's law because the transistor density is increasing. So this is about the processor. Another example that I can give you is about supercomputing performance. So this is like a supercomputer. The definition of a supercomputer is the top performing computer of a given time. Like today, let me just make this as. So today there is a top supercomputer is called as Fugaku. It's based in Japan and it has a performance of 442 petaflop. So what does this 442 petaflop mean? What does that petaflop mean? Flop means floating point operations per second. And peta, like you have mega, like this mega is 10 raised to 6, then mega, giga, tera. So that makes it 10 raised to 15. So 442 into 10 raised to 15 and 10 raised to 18 would be exaflop. So almost half a exaflop is the performance. So now how is it measured? So this is measured. You have a system that is installed in Japan. There is a program called as High Performance Linpack HPL. So it's a benchmark. So a benchmark is a program that is run across different computers and each of them it gives some number and that number is the performance, measures the performance of that particular computer. Like suppose you have a banking server, then how many transactions in the database can happen? That could be a metric for that. So many transactions per second will be the benchmark for a system that uses databases. However, here supercomputers are used for scientific and engineering application. And the core of this such application is floating point operation because you need very high accuracy results. Hence, to measure that, it's measured in flops, petaflops, teraflops, etc. And here the graph here shows how the performance has increased over a period of time. So this is the entry level supercomputer, that is number 500 as you see here. And this is this the other one. And this gives the 500th number. Okay, so this is a 500th number and this is a number 1. And if you notice here, this as I had mentioned here, this list is published twice a year. So if you notice here, you see a computer which is at number 1 is remains at number 1 for let's say 2.5 years. Then a new one comes, then this remains for 2 years. Like this, you will find if the same dot is this triangle is horizontal, that means across few list like two instances is 1 year. So here for 3 years the same computer remained the top supercomputer. Another thing that you can find out is that the supercomputer which is number 1 here in let's say 1994 it started. If you take a horizontal line here like this, by let's say 2003 it would become number 500 because better and better supercomputers have come in. So what are we trying to indicate through this graph? That improvement in performance is constant. Every whatever time you can take, 1 year, 2 year, or whatever time scale you take, you are going to get computers, CPUs with better and better performance. So that is these are the two instances which show that the computing performance have increased. And apart from Moore's law, the features that architects have added has contributed to the growth in performance. So I kept talking about performance. Why is it so important? Because that's what matters. So you pay a price to get a performance. Okay. So beyond what Moore's law kept improving, that was an inherent change or inherent improvement that kept happening. They processor architect look at different features that they can add, that they can incorporate in the newer members of the family that they are designing. So what is the motivation for that? So performance is the basic motivation, but there are other considerations also. Some of them are listed here. There are some features that the higher level language supports. Okay. So the language that you're using, let's say you are using C or you are using Fortran, or maybe a newer language comes in. And some of you might have seen that there are some things which are used for in AI related application. There are some frameworks like TensorFlow, which are related to AI related framework. So now the industry is making TensorFlow processor. Why? Because the features that the higher level language gives to the programmer, mapping of those features into the architectural features is one of the way by which improvement in performance can occur. Okay. Then this is like there is a need that is coming from the higher level languages, which are indicating that these are the kind of constructs like object oriented programming was came after simple C programming. C, Pascal, Fortran kind of languages existed. So the newer languages that they demand, they give some facilities to the user, and they in turn demand efficient mapping of those facilities, or I would say the features that the language offers from the hardware. So the architects of processors have to live up to those expectations and see how those can be serviced efficiently by the hardware that they are designing. Then what happens is the CPU starts running faster. You would know that you can also look at a graph which says how processor frequency has increased over here. Like the first 8086 that came out used to run at modest 4.3 megahertz. Today you have processors that run in excess of 2 gigahertz, so 3 order increase over a period of time. But memories, they have not become so fast. So memories are going to be slower. So they create a bottleneck. CPU is running at full speed. It needs data from memory. Memory is slow. CPU expects it let's say in 30 nanosecond. The memory cannot give it in less than, let's say, 60 nanosecond. So what is to be done? Something has to be done about that. So there are some features that are incorporated which try to hide the memory latency, like use of cache memories and other things, large number of registers. So some of these methods are used to avoid the problems that are faced due to mismatch in speeds and other thing. Similarly, I'm not sure whether this was covered in the morning, but in a pipeline processor, whenever a branch takes place, that means, let's say at address location 100, you have a instruction called JMP 200, which means that the next instruction after execution of instruction at location 100 needs to be at location 200. So this is a branch. So whenever such a branch occurs, the pipeline has to be flushed. And when pipeline is flushed, at that time you lose work because it inserts bubbles in the pipeline. Possibly this was covered in the morning, and I'm sure this branch prediction was told. I heard that. So to overcome branch delays, you use branch prediction. So basically, when you try to improve the performance, you will hit some bottlenecks, and those have to be intelligently overcome by means of incorporating certain features that elevate those problems. You may not be able to totally uh, get over them, maybe, but you will be able to make sure that their severity is reduced. And last but not the least is to increase the parallelism. So that is what is the crux of today's discussion, that how parallelism comes into picture. So over the years, starting with simple von Neumann architecture, that fetch, decode, execute, write back. That was the kind of things that von Neumann indicated, that a stored program should be used, and that's what all the computers in the past 60-70 years are following. So that was the beginning. Maybe it happened with somewhere in the mid 40s or early 50s, and it's still continuing. And I cannot but stop from repeating that there have been transistor budgets which have been aiding it, and improvements in VLSI design technologies have fueled these improvements in technology. And VLIW is one such technique that is used to improve parallelism while executing the instruction. Okay, so here is one table that tells how things have improved. Like the first member of the Intel x86 family came in 1979. So it has a modest 29,000 number of transistors. The feature size. So what is a feature size? That's the thinnest line one can draw on a silicon. Like you have, I'm sure you know that the transistors made, or the MOSFETs, field effect transistors, are made of P and NP kind of semiconductors with two PN and NP junctions, or vice versa if it's an NPN transistor. So the thinnest line you can draw, thinnest line was as big as 3 micrometer, that is 3000 nanometer, and the size it occupied was about 33 square millimeter. So it's almost a square that they make. Fast forward to 2021. One of the latest chips is Apple M1 Max. It has got 54 billion transistor. Okay, so 1000 has 3 zeros, billion has 9 zeros. So 6 order increase. That's phenomenal. Okay, and the feature size reduction from 3000 to 5. That means the smallest line drawn on silicon using P or N type of material is as thin as 5 nanometer, and the size has also appropriately increased. So if in 1980s you had few thousands of transistors available for implementing a logic, and now you have 6 orders more number of transistors, obviously the features are going to be different, and that is why there has been improvement in performance over years. And this table gives us a small idea about what has been the leap in the feature size, the transistor count, and die size. Now let's look at the background, some background information that will help us in understanding the VLIW. So first thing is that you have to take a holistic view. Okay, though you are designing a processor, one has to see its purpose, why we are designing this processor. Okay, that is because somebody is writing a code in higher level language. So this is simplest thing that I have taken, that a language like C or formula translation that has been existing for a few decades, and processors have microprocessors have come since then. So you have a higher level. This is one flow. Okay, so now there can be some things may be clubbed together, like some compilers may directly generate machine language program. That's perfectly fine. But just to make matter simple, and to make you understand that there is something called as assembly language, I have included this as a flow. That you have a higher level language which you use a compiler like GCC or something, and you compile the code. It is in this example that I have stated, it generates an assembly language code out of it. Okay, like you have statements, like you declare variables, then you write a main loop, and in that main loop you do some implement some algorithm, let's say sorting 100 numbers or something like that. So that you give it to the compiler. Compiler first checks that there are no compile time errors, your statements are correct, everything is correct, and then it will generate the assembly language code. This assembly language code is given as an input to the assembler, and the assembler generates machine language code. So now we are not talking about loaders, linkers, libraries and all to make matters simple, and straight away you get a executable code which is in machine language, and that in turn then now runs on the processor. And when it runs on the processor, what is the interface between the machine language and the processor? That interface is called as instruction set architecture. So if you are studying a processor architecture in very seriously, then you should understand the implications of instruction set architecture. So instruction set architecture is the interface through which a program interacts with the processor. Okay, so an instruction set, as the name suggests, just a minute. As the name suggests, the first two words are instruction set. So it has a set of instructions. So that's very simple to understand. Let's say you take 8085 or any other microcontroller. It will have a data sheet in which all the instruction that that particular processor can execute are listed. So instruction set is a set of instruction, but when you add the word architecture, it also includes few more things like how many registers are there, what are the addressing mode, where can the operand come from. So all these details about how the processor is going to execute those instructions, that is all supported, that is all indicated through this instruction set architecture. So don't confuse instruction set architecture as just as a set of instruction, but it goes beyond that by including other things like what are the different type of branches that you can take, whether it's relative, how are the flags affected. So all this functionality of a particular processor is defined through this instruction set architecture. So this is very key thing, very important thing for us because all VLIW or Superscalar that you saw, they will all be trying to make sure that the instruction set architecture is made efficient. So moving ahead. So now in the previous diagram, we saw that we have finally the aim of a user is to write a program. Let's say, as I mentioned, you have written a program to sort 100 numbers and make the processor sort a number. You have a set of 100 numbers that you have given as an input, and the output of the program, let's say it's in a file, 100 numbers are listed in random order, and when you get the output file, you get those numbers sorted. Let's say this application is that a teacher is using to rank the students in a class where the input is a total marks obtained. So it's a table consists of roll number and total marks. And then the output that you get is roll numbers and mark, but sorted in descending order so that the teacher can say declare who is the rank 1, 2 and 3. Let's say that's the application. So now let's see how does that get mapped onto a processor. Okay. So as we saw in the previous slide, that programmers would use higher level programming language. So they will, let's say, write a statement like this, that the new value of A is the old value of A to which value of B is added and the sum is incremented by 1. So let's say this is what the programmer writes. Okay. However, as we mentioned, the CPU can understand only machine language or the binary code. So please remember that machine code is directly mapped to assembly language. That means for every statement in assembly language, there will be an operation code which will be followed by the operand. So you have an assembly language is one-to-one, has a one-to-one correspondence with machine language. So you can use this word interchangeably, but assembly language uses mnemonics and labels. It's very close to, I mean, understanding it English, whereas machine language is a sequence of ones and zeros that you all know. But the reason for writing here and or assembly language in parenthesis is that there is a one-to-one correspondence, whereas for one statement like this, there may be a series of statement in assembly language. So there is no 1:1 correspondence between higher level language and machine language, but a statement in higher level language results in multiple assembly language statements or multiple instructions. So we saw that how it is converted to assembly language through use of compilers, linkers, loaders, etc. And assembly language consists of a series of instructions. So let us see how. Let's take the same example. Now in this case, when we say add is a mnemonic, and A and B are the operands. In this case, A and B are the registers. So we are talking about a CPU that has two registers called A and B, and we are assuming that the values of variables A and B, which is a part of the higher level language statement, they are, for sake of simplicity, they are in these two registers A and B. So what do we tell through these two instructions? We accomplish the following. Register A has value of A, register value has value of B, and when you execute this instruction add A comma B, then register A gets replaced by sum of A and B. So A will be getting a value which is obtained when B is added to it. And then next instruction is increment A, because to correspond for this +1. So a statement like this, a very simple statement like this in higher level language has resulted in two instructions being executed on the CPU. So typically each instruction has two parts. One is an opcode, another is an operand. So in this example, the opcode, it specifies the operation to be performed, like add or incorporate or inc, that is increment, and the operand specifies where to find the data. Like in this case, the data is found in register A, or increment is a urinary operator, so it just needs one operand, whereas add is a binary operator, it needs two operands, so it specifies A and B. So what we have seen here is that the higher level language statements essentially get converted into a sequence of assembly language statement which get mapped onto machine language, and that binary code is executed on the CPU. Okay, so for this to happen, there is, in a simplest form, there is an ALU. Okay, so we saw there is an instruction and there is an opcode. So the instructions have got their corresponding operands. So you will say this is the operand part, and sorry, this is the opcode that is there in the instruction. So as the expansion of opcode is operation code, what is the code of that operation to be performed, like add in the previous case or increment, and then on that you get, corresponding to that you have data. So what is data in the previous example? A and B for add, or A as a operand for increment. So once that is done, so every instruction will have an operand and every instruction will generate result. So that is what happens in the heart of that processor. So when you say an instruction is executed, it performs certain operations. So this particular operations involve ALU. Some of the instructions may not involve ALU, like jump. Jump instruction only changes the flow of program, or a conditional branch like jump on no carry. Such instructions, they don't use ALU, but they will use some other unit inside the CPU. We'll see more about that later. So like in this case, the data is two operands are 2 and 2, and the opcode is plus, which is shown here, add, and you get the result. So that's how it works. So if you just zoom out of that, if you zoom out of that, you will find that this opcode, that is instruction, and the data that it operates on is stored in the memory. And from there, the CPU knows where to find instruction, the CPU knows where to find the data. So now that we are here, I'm not sure whether you are getting bored or something. Let me ask one question. Like this instructions, where should the next instruction come from? So put it in the chat box. What is the pointer to that? So what block inside the CPU points to the next instruction to be executed? If you know that, just put it in the chat box. I will not be able to see it because my screen is showing the presentation, but later I will see whether you have answered it correctly. Okay. So there is a mechanism to fetch the next instruction. When it fetched, it goes temporarily into instruction register. Then after it comes there, the next block finds out what is to be done, like add, subtract, multiply. What is that it wants? Jump. What is that the instruction is asking the processor to do? Suppose that it's an arithmetic logic instruction, then the control unit finds out, okay, what is to be added? A and B are to be added. Okay, A is here, B is here. Through this control signal, it will enable A, it will enable B. A and B will appear at the input of the ALU. Then one of the signals will tell ALU, you need to add these two numbers, and the result will again go back to one of the register. Now the data registers are small in number, but the data is large, so data is maintained in the main memory. Whichever operands are required at a particular point in time, they are brought in and used as an input to the ALU. So this is how this an instruction executes. So now I said that instruction set architecture is an important thing for us to understand the overall architecture of the processor. So here are some details about it. So I have already mentioned to you that in the diagram that I showed, the machine code, when it gets inside the CPU, that is where the ISA is. So it is a interface between hardware and the software, that you can say broadly. If you want to say it more specifically, it is between the programs and the processor. So the program is the software and processor is the hardware. So the programs run on processor, and they talk to each other through this ISA. Okay. So here let me tell you that whenever a new processor is designed, the first thing that the processor designers, the software and the hardware designers, they agree upon is the instruction set architecture. So they decide. So when the instruction set architecture is designed, at that time, that you can say that the specification of the processor is freezed. And once the ISA is freezed, the programs can be developed without knowing how the actual hardware is, because the hardware designers have agreed to treat ISA as an interface through which they will talk to the program. Similarly, once that is done, the processor designers then do not care about what program will be written, as long as the programs that are written, they use the same ISA. So that's where the paths become independent in a traditional design of a processor. So another fallout of ISA is that it ensures software portability. Like I mentioned to you, X80IA32 is an instruction set that Intel made for 80386 processor. Okay, once they did that, 486 that they made, it supported all the instructions that 386 supported. Then they made Pentium. Pentium would run all the code that was written for 386. Pentium 2, same thing. Why? Because the basic instructions are same. Newer versions of processors may add new instruction, but they will continue to support the instructions that were there in the previous member of the family. So that's why program developed once will work during the lifetime of the ISA. Okay, but it has a disadvantage also. Migration to new ISA is very difficult. An example of that is Itanium. I am going to describe Itanium as a VLIW processor. So if the software is available for an old ISA, it is difficult to move over to the new processor architecture. So that was about ISA. Okay, so now the ISA also, there is an important aspect that you need to understand is what is called as dynamic static interface. This will keep appearing when we talk about VLIW. Okay, so why we call it as dynamic static? That is because I gave you an example earlier, the output of the compiler, forget the assembler for the same time. You can say the compiler assembler are a part of the same ecosystem of the tools, and the output of that compiler is given. The output of the compiler is a machine code, and that is what is given to the processor. And what happens before the program, the machine language program is generated, is done by the compiler. So we will call it as static. Meaning, to give an example, let's say you write again take the example of sorting 100 numbers. You write a code. You write the code once, debug it, test it. Now once you have written the code and the binary is available, you can freeze it. And then the same program can be run by 10 different teachers, each giving different data. So the program is still same. It is compiled and it is static in nature. The image of the program doesn't change, but the behavior of the program, behavior of the CPU changes. Why? Because the data that you have given is different. So what happens inside the processor is dynamic in nature. It depends upon the conditions at that time in terms of the data that you're using and other things. Whereas the program once compiled is static in nature. The image of the code remains same, but the behavior of that program will change. That means it may in some cases it may take a few nanoseconds to run. In other cases it may take more time or less time, because that's a dynamic behavior which happens at the runtime. Okay. So now this ISA, it can be, we know that ISA sits between higher level language and the processor. So let me give an example of what I'm trying to say through a diagram. Okay. So I'm sure all of you would have heard about this CISC and RISC. CISC stands for complex instruction set computer and RISC stands for reduced instruction set computer. In case of CISC, the instruction set is complex, as the name suggests. That means that the features that you get in the CISC processors, the instructions that you get in the CISC processors are complex. Like you can add a location data which is in the memory into a register. Such kind of complex instructions are supported. So now what is this DS1? It is separating the higher level language program from the hardware, and in between there are various levels. So this arrow is small, whereas the light blue arrow is long. That means this DS1 dynamic static interface is closer to the higher level language program. That means this arrow being small, the program has to take little efforts, whereas because the instruction set is complex, the hardware has to put in lot of efforts to execute that complex instruction set. In a crude way, I can say that the program is telling complex things for the hardware to do. As a result, the task of the hardware becomes much difficult. So that's why this arrow is long. Now reduced instruction set. In reduced instruction set, there are small number of instructions which are executed almost in one cycle. They are all simple instruction. If that is the case, then that's the reason why this light blue arrow is small, because the hardware has to execute only simple instruction, that too very small in number. But when you have small number of instructions, any task that you want to accomplish, the compiler has to work hard because it has got very less number of instructions at its disposal. So when such a thing happens, this dark blue arrow becomes long. That means work of the compiler is complex. Work of the hardware that it does is simple. Reverse of this happens in case of CISC. The job of the compiler is simple, whereas the job of the hardware is complex. Here it will be pertinent to say, I will explain how that happens later, is VLIW sits right in the middle. Meaning now if you see here, this is small, this is large. This arrow is small, this arrow is large. That means one of the two has to do more work. Whereas here, approximately both of them have to do same work, same amount of work. So that is why VLIW is supposed to be a progressive architecture, that it tries to have a good balance between the work that the compiler does and the work that the hardware does, that the processor does. Okay. So this is one point that you should note, keep in mind, we will use it later. Okay. So this was the background, that how things work, how are the basic execution. We saw that how a higher level language program gets translated into machine language, and we also saw that there are two types of architecture when you look at the instruction set, complex and reduced, or you can say complex and simple. and in both of these either the hardware has to do large work like in RISC, or the software has to do large amount of work as in case other way. Software has to do large work in RISC and hardware has to do large work in CISC. So, and that's where VLIW tries to strike a balance. So now coming to this is just again a refreshing. You have studied this in the morning. So what are the things that the architect does, the processor architect does to increase the single CPU performance? So first thing that we should note is that a single CPU, single stream of code. That means a set of instructions which is a single stream vis-a-vis multi-stream that will occur in some of the cases that shall explain later. So in a simple form, there is a sequence of instruction. I showed you to add a comma b, increment a, then it could be load something, then add something, store something, a sequence of instruction. So what is that they do? Like 8085 was a 8-bit processor. 8086 was a 16-bit processor. 80386 is a 32-bit processor. i3, i5, i9, they are 64-bit processors. So the successive generations will use more number of bits in their in the data. Okay, so these are multiples of 8 and these are some commonly used. So the conclusion is simple. You have more number of bits, so these can be handled per clock. That means you can handle bigger data. So if suppose your actual floating point number is, let's say, 256 bit, because you want good accuracy, suppose it is 256 bit, then if you had a 16-bit processor, then you would have been required to do 16 times the operation to handle 256 bit. But if it's 64, then you have to do the operation 4 times, because 64 plus 64 128, 128 plus 128 256. So only 4 words, 4 times you'll have to do. But that's how, when the number of bits has increased, the number crunching ability that the ALU can handle per clock increases. Second thing that they do, processor architects do is, or that is anyway keeps happening, is increasing the clock frequency. I already mentioned to you that 8086 had a clock frequency of about 4.33 megahertz, and now it is like 2 or 3 gigahertz. So when you have increase in frequency in a unit time, more instructions are executed because they are coming in fast. The clock period has reduced, the frequency has increased. However, what should be noted is the power consumed by the CPU is proportional to the square of the frequency, meaning you double the frequency, power will increase 4 times. And this is not a good thing to happen, because every CPU has a what is called as TDP, rated TDP. And this cannot be exceeded. You must have seen CPUs having fans, then they have some kind of metallic things called as heat sinks to dissipate power, because all the higher the frequency, more is the flow of current, more frequently is the flow of current, and that's how power is consumed. So you cannot increase clock frequency beyond a bit, you cannot increase the ALU width beyond a point. Then what is that is done? The most obvious way when you hit both of this is to introduce parallelism. And how will you introduce parallelism? By means of replication of certain functional units. So what are those functional units that are duplicated? I will explain that slightly later. Okay. So one of the ways of doing it is either you can replicate the units that perform the operation on multiple data elements. So those are called as single instruction. So instruction is same, but the data items are more. So they are called as SIMD. And other variation of that, wherein you can have multiple operation, that means different operation, they are happening on different data elements. So they are called as MIMD. So if you have studied in second or third year in computer organization, you would have studied Flynn's classification, single instruction, single data, then SIMD, MIMD, and multiple instruction, single data. These are the 4 classification that he did. Okay, so parallelism is the key now for improving the performance, because we will acknowledge the fact that we have increased the width, increased the clock, and we have no scope for that. Okay, so there are a couple of things that can be done. In the morning you studied pipeline, that is the new instruction enters every clock, and the number of pipeline stages, that much parallelism is available for you. Other thing that also you also studied in the afternoon session was superscalar. So in this, what is duplicated? We said that you have to replicate the functional unit. So in this case, we replicated the stages. We broke down the long stage into multiple number of stages. Whereas in superscalar, only the execution unit is duplicated. Okay. So now superscalar, Pentium was a superscalar architecture. 486 was a scalar architecture. And as I mentioned to you, that all instructions of 486 will run on Pentium. So the change that they made was inside the processor. So what they did was the instructions are still same, sequential instruction inside, but because there are multiple execution unit, they can be issued in a multiple way. I will show you a diagram how it works. While this is instruction level parallelism, pipeline and superscalar, another type of parallelism that you see is SIMD instruction that I mentioned to you, wherein we achieve data level parallelism. I will not spend time on this. You had got an entire lecture on this. So this is the time scale on which instruction I1, I2, I3 are executed. In a non-pipelined architecture, this fetch, the instruction I2 will be fetched after the first instruction is completed. But because it is pipeline, once this instruction is fetched and it goes for decoding, the fetch unit is free. Who uses it? I2. And in the third cycle, T3, instruction 1 goes for execution, instruction 2 goes for decoding, and a new enter I3. Instruction I3 enters the queue. So this, in the morning, Professor Govindrajan showed you a pipeline with 5 stages. But one can have with 4, 3, whatever, it depends upon how it has been designed. But fetch, decode, execute are the basic 3 cycles that any processor will have. It may have more number of them. Some of the Intel processors have got 20 stage pipelines and more than that. Okay. Then superscalar. This is what I was trying to explain in the previous slide, that the fetch unit still fetches sequential instructions. Okay, so the instructions are sequential in nature. However, inside the execution units are more. Like in this example, there are 2 execution units. So remember that this instruction that has been compiled by the compiler, it is not aware of superscalar. Okay, like for VLIW, we kept saying that it's an interaction between the compiler and the processor. They share the load. They know each other well. Whereas here, this program, let's say, was written for 386 or 486, which is a superscalar processor, and this, let's say, is a Pentium processor. So the difference between 486 and Pentium is that there is, like, I wouldn't say there are more than one execution units. Okay, so how much Intel never told, but for argument's sake, for simplicity, let us assume there are 2. So now this I1 and I2, they are scheduled on 2 different processors, provided there is no dependency between them. I think this has been adequately covered in the morning, but in a simple form, if there are no dependencies, you will have odd instruction coming on one, even instruction coming on another, and this will keep on happening. And the clock, the cycles per, or the instructions per cycle that we said some time ago, that will become 2, because every cycle you are executing 2 instructions. That is ideal, but in practice it will not happen because of several reasons. Basically what we call as due to control dependency and data dependency. Okay, so this is how that superscalar looks like. You have a memory, from there you fetch an instruction, and you also studied that an execution unit internally is pipelined, and then essentially the pipeline will work, but 2 separate pipelines will work, and 2 execution units will execute multiple 2 instructions per clock. Okay. I will also give a brief reference to SIMD instruction. So this we saw in the some time ago, that the instructions operate on their corresponding data. So suppose you want to add three numbers. A0 is added to B0, A1 is added to B1, and A2 is added to B2, and giving correspondingly C0, C1 and C2. This plus here, these three addition are three instructions here, and these numbers, they are coming in pairs from as a data. In case of SIMD, what happens is that the instruction is same, but every instruction has multiple operand and the same single instruction I, but multiple data. So multiple data comes in, and thus what happens is you have a packed data A0, A1, A2 in one you can say word, three bytes of data is there. Another has got another 3 bytes, and in one shot, because you have multiple execution unit, you get the so in get the three results C0, C1, C2. So notice the difference. Three instruction I1, I2, I3, whereas just one instruction which operates on multiple data. So this is how it works. Like in a normal processor, you have a 32-bit register, whereas in a SIMD, you have got 128-bit register. So internally, they are divided into four 32-bit words. And as a result, the instruction that comes in, it works on four different words, right? So that is how the SIMD instructions work. So we are almost to the half of the session. So any questions? I'll just check whether
I
there are
have one
any.
question, sir.
Yeah, tell me.
Is there any particular reason why Intel's compiler like does not use the superscalar advantage?
See, the compiler cannot take advantage of superscalar for a simple reason that the compiler is not aware that there is superscalar. Let me put it this way. I just now mentioned that 486 is a scalar processor, one execution unit. So that is easy to understand. A single stream of data is coming in that is being executed by the one single execution unit. I hope that is understandable. So it's like stream enters, stream gets executed, instructions are expiring, they are retiring. Now imagine that because of the Moore's law, we got more number of transistors. So we got double the number of transistors. So how to use it? What we can do is we can have two execution units. In the simplest form, what will happen is all odd instructions here, all even instructions here. But who is checking that dependency? The issue unit. If you remember in the diagram that I showed, this is the decode issue unit. See here there is a single stream, but here they become multiple stream. How? Why do they become? They become because there are multiple execution unit. And what is the check that it is doing? It is checking whether there, I think this must have been covered, so I didn't get into details of this.
Yes, sir.
But it checks the dependency not only between these two, but those which are in the pipeline, whether there is any hazard, control hazard or data hazard. So to answer your question, the compiler cannot take advantage because compiler is not aware, because that parallelism who is incorporating the decode issue unit, because there are multiple execution units. So it's done here. That parallelism comes from here. Here is serial, sequential, but parallel here. I think there are some more things in the chat box. Let me have a look at that.
Sir, can you give one example for VLIW?
We are coming to that. Now we will start. Okay, all that will start. Okay, so there is a question from Naman. He asked why migration to new ISA is difficult. Okay, the reason is as follows. Uh, if you would have realized that every 3 year, like suppose you have bought a computer, you will definitely throw it away after 3 or 4 years because better performance hardware is coming in, and we are willing to pay for that. But suppose you have bought AutoCAD for let's say 50,000 rupees, and then you come with a new hardware. Somebody comes with extremely good hardware, but they say that you will have to throw that AutoCAD. You will have to buy another one because they are not compatible. It's different product altogether. If you say that you are not going to buy that new hardware, that's precisely what happened. Why Intel had said that Pentium 2, Pentium 3 or Pentium 4 is going to be the last Pentium, last x86 processor. We are all going towards Itanium. I will tell some details about that later. But nobody, it came in the market, but nobody was willing to move over because all the software investment that they have done. See, AutoCAD is a small thing. You have big things, software systems running on existing hardware. It is easier to just change some of the boxes, but let the storage and everything remain same, because you are just taking a downtime of half an hour, just changing the boxes, and then it's suddenly becoming faster. That's much easier to do. But somebody says now shut it down, everything has to be put afresh. That has a problem. Okay, so that is the reason why migration to new ISA is difficult. Okay. So a lot of you have said PC, that is program counter. The answer is correct. Okay. So thanks. So any more question, you can unmute yourself and ask now. Okay, so Venkatesh asks, when we have VLIW instruction, how will it affect the memory architecture or design? Okay, so I will explain that. Okay, will that be if larger bus width then power problem? I will explain that. Okay, so we will come to all VLI. So hold on your VLI related questions. Let me just tell about what this VLIW is. Okay. So any more questions? All right. So I will move over to continue the presentation. So in this context, now we have to see VLIW. So on one side, we have Superscalar as a mechanism of increasing parallelism inside the CPU. On other side, we have this dynamic static interface, which is trying to be skewed. One is towards the hardware, other is towards the software in terms of RISC and CISC. Now that's how that was the time when Joseph Fisher, he was a computer scientist during his PhD. He was a compiler designer, and he was writing an optimizing compiler, and that optimizing compiler was working on the concept of trace scheduling technique. So basically what that trace scheduling technique tries to do is try to schedule the instructions in such a way that they get executed without any wait or a delay inside the hardware. So that's putting it very crudely. Okay, so he was designing that, and none of the hardwares that was available then was suitable for efficiently doing this trace scheduling technique. And that's how he came out with this idea of VLIW. So what is that? We will see in the next few slides. However, though he came out with this idea in 1983, if you go back in time, then you will find that there was a company by name Floating Point Systems, who as early as 1975 made one hardware unit called as FPS 120B. So now this was not a computer by itself, but it was designed to be attached to a host computer like VAX. VAX was one of the prevalent computers at that time. And what it would do is VAX was not so good at a floating point operation. So this you can say that it used to accelerate floating point calculations, and it could do multiple floating point calculations in the same clock. And it used this concept of VLIW, which I'll explain later. Okay. And then subsequently, in fact, Josh Fisher, he started this company Multiflow, and there was another company called Sidrome. They also got lashed onto this idea, and in the late 80s, I think 87 and 88, they came out with VLIW processor. This one came out with Trace. Multiflow came out with Trace. It's obvious that it was made by Josh Fisher and his team. And Sidra 5 was, and it was a family. Sidra had a family, and they came out with that. Okay. And then there were some small efforts subsequently. The biggest effort to making a VLIW processor was made jointly by Intel and HP. Actually, HP had a processor called PA-RISC. Okay, so in fact, a RISC processor, RISC architecture is more amenable to be converted into VLIW than CISC. I don't have time to explain the difference between the two or why is it so. But one of the attributes is that RISC processors have got a fixed word length. I think it must have been mentioned in the morning by Professor Govindarajan. whereas CISC has got a variable. So when it is fixed, then it becomes easy to convert into VLIW, as you shall see later. So HP was working on PA RISC, and Intel thought of Itanium. So they joined hands, and HP said we will make the compiler. Intel said we will make the processor, and they coined a term called as explicitly parallel instruction computing. So explicitly parallel, why is it so? It will be evident when I tell you about that. But it was an implementation of VLIW. So this is what has been the history of VLIW. So now with that, let's look at what are the basics. How does this architecture work? Okay. So the first thing is that it has considerable number of execution units, starting with 5 can go up to 30. Okay. So remember that these execution units, I'll give example of that. They are not symmetric in nature, meaning every execution unit is not same as other. They will form certain specific purpose. Then we will call it as an instruction or an opcode or a control word length. All of them are interchangeable terms of length 16 or 32. Okay, so one unit has a word length of 16 or 32. For argument's sake, let us take it as 32 to make it simple. And so one 32-bit word of instruction will work on one U. So the maths is simple. One instruction word uniformly is 32. That goes on one execution unit. There are multiple execution units, and you will have an instruction word which will have many such units. So if it's 1024 is the word length of an instruction word of a particular VLIW processor, and 32-bit is, let's say, its word length, then you divide 1024 by 32. So this is 10 and this is 5. So 2 raised to 5. So 32 into 32 is 1024. So you will have in one instruction word, you will have 32 instructions. I hope you are getting it. And these 32 instructions can straight away go on to 32 execution units inside the CPU. I mean, this is a theoretical number. All right. So with 32, you may not have 1024. With 32, you may have something like 512 or 256. So something like 8 or 16 such units, they operate on the execution units. So now please compare it with scalar process, superscalar. The stream enters, it is then assigned to a free execution unit after checking dependency. Now this task is difficult to do in real time because you have very limited number of clocks to do it. Taking the decision is very in a dynamic way is extremely difficult, and if the number of execution units increase, it becomes all the more difficult. But what if this task is taken by the compiler? Then the burden will be removed from the processor. So now what is the how many execution units are there? What are their capabilities? All that is known to the compiler. So if you notice here, the burden of assigning the instructions in an instruction word to the execution unit is determined by the compiler at the time of compilation, at the time of optimization. This is the crux of VLIW. If you understand this, then you would have understood VLIW. Now, because most of the logic inside the processor was required for deciding this, how to schedule, when not to schedule, when to wait, that is all gone. Which means your processor's issue unit has become less complex. That means overall complexity is reduced. So what the processor designer can do with VLIW is it can increase the clock speed, it can add more number of units, or do both. Okay. So this is how VLIW, this is the gist of VLIW processors. Okay. So to elaborate it further, let's look at the VLIW instruction word. You take one instruction word, it encodes multiple opcodes. Okay, so it will have multiple opcodes in which, and all of them are issued together. So if you compare it with the superscalar, a single stream was entering, and it was getting divided into execution units. Here, a parallel stream enters, and what the issue unit has to do is simply give it to the corresponding execution unit. Nothing, no schedulings to be done by the issue unit, for a simple reason that that task has been taken over by the compiler. Each of the opcode and their operands are assigned to the specific functional unit. Just hold on for a minute, I will show you that in the next slide. Okay. And the length of instruction words, how many operand, how many opcodes and how many units in one word is proportional to the degree of parallelism. Like it would be 3, 4, 5, 6. So many, how many instructions can be executed in parallel, that is degree of parallelism. And that also depends on the functional unit. Okay. But sometimes what happens is in some cycles, don't assume that all the instructions word have got all the opcodes populated. No. In the worst case, one word may have only one instruction. Why? Because whatever was supposed to occur in the next slot, there is some dependency because of which it cannot schedule an instruction there. Okay. So this is how it looks like. That remember two things most importantly, the register file is common. Okay, so these are the execution units: integer arithmetic logic unit, load store unit, okay, floating point add unit, floating point multiply unit, branch unit. Okay, actually this load store unit should be here. Actually this should be here, integer ALU should be here because we are connecting it to the main memory. That means that's why this load, this is a mismatch here. This should have been here and they interchange the space in a hurry. Okay. So what does this load store unit do? It can fetch operands. It can store operands. What can FP add unit do? It can add floating point numbers. What can this do? It can multiply two numbers. What can this process? Branch. In the morning you saw how branches are processed. All right. So these are the functional units and there may be not just one of these. Like in Itanium you have, let's say, 4 FP add unit, 4 FP multiply unit, and then as many. And don't think that if there are 30 units, you can have 30 instructions in parallel. No, the degree of parallelism could be less than 30. That depends upon dependencies and so many other things. So we'll not get into those details for sake of paucity of time. But this is an important thing that you should look at, that there are multiple instruction in one word. Every instruction is assigned to one unit, and the how many words can come, one word can have how many instructions, it depends upon the degree of parallelism. Okay, and it's not necessary that suppose the word, one word has got 6 instruction, it is not necessary that every word will have 6 instruction. There may be some missing items. Why? Because of the dependency, because of the scheduling algorithm. Okay, so here it makes it clear. In case of superscalar, the parallelism was coming here, but here the word itself is coming with parallel opcodes. And what does the fetch unit do? It simply issues it. It doesn't have to do any decision. Like if this is I1, this I1 is going here. If it's IN, the IN is going here. That's it. So that is why the complexity is removed. Okay, so the issue is very, very simple. Okay, so now I will again tell you how does that, how does now it compare. Last time we saw pipeline and superscalar. Now how does VLIW fit in here? So compare it with superscalar. There are multiple execution unit, that is same multiple execution unit. What is the difference? Difference is instead of sequential instruction, there are multiple instructions packed in one word, as is seen here. They are already packed. Who has packed them? Compiler. And where are they lying? They are lying in the memory. Okay. So Venkatesha had asked a question that does this become wider? Yes, it does become wider. Does it need more power? Yes, it does need more power. But overall the power is saved. Why? Because this unit was much complex and it was taking much more power than the power that has to be expanded in fetching multiple bytes from the memory. Okay, so that is how it works. So now let's see what is that the compiler does. The role for compiler is very significant as compared to the superscalar. For superscalar, there is no change in compiler from scalar to superscalar. Okay, what is the important task? it performs the important task of scheduling and packing instructions in one word. Okay. So again, before this VLIW compiler starts optimizing, it gets a serial code because we are written a serial program that gets converted into serial code. Now what does it do? It will take a bunch of instruction, see which instructions are capable of executing parallel. There is no dependency. It will put them, it will pack them together. Now such independent instructions are grouped together, but that's not all. It will also see that there are no dependencies. So that's one part. It will also ensure that required operands are available. Suppose the previous instruction is loading from the memory. In one clock, you load data from the memory. This instruction of loading from the memory, which is slow, may take 3 clock cycles. If the next instruction is using that data, then it cannot appear in the subsequent instruction word. It will have to give a gap of 3 instruction word because those many clocks are required for the data which is being fetched by this load instruction to actually be there. So what is that the compiler is doing? It has a stack of serial instruction. It is making multiple piles of those stack and putting it in such a way that there could be some bubbles in between, but making sure that there is no dependency, and when an instruction comes for execution in the CPU, the operand is available. Okay. So let me just compare the two. Now that we are migrated or we are trying to improve from Superscalar to VLIW, let us look at the instructions that are in the code that goes on the processor. So that is same. There is no change. It fetches sequential instruction. However, it converts that into parallel. Whereas here, the instruction themselves are coming in parallel. That is the first difference, major difference. How are instructions assigned to the execution unit in Superscalar? Dynamically. Who does the issue unit? It checks the dependency. Whereas there is nothing like issue unit here. Why? Because it is already done statically by the compiler. That is where the static dynamic interface comes into picture, and that is the significance of VLIW. Instruction word length, it is native to the CPU family. Whatever is the instruction word length of 486, same is true for Pentium. Whereas the typically it will be a packed instruction. How many execution unit? 2 to 4. You cannot go large because the dynamic scheduling becomes very difficult if the number of units are more. But here you can go. Why? Because there is nothing like issue unit. It is straight away taking and dumping it on the execution unit. How has it evolved? 486 become 586 or Pentium, or that's how a feature was added inside the CPU. Everything outside is no change, whereas it is designed from scratch. So here it may be a good time to take some questions because we have seen some important aspects of VLIW and I want you to understand this. So if you have any question, let me just see what Karthik has asked. If one word can have 32 instructions and these are being fetched from IMS, how heavy are the penalties for cache misses? Okay. They are definitely high. In fact, one of the problems that disadvantage of VLIW is the scheduler. See, remember the scheduling is done by the compiler. The compiler will assume average delay, some average delay. But what will happen is because it is average, actual delay could be faster, actual access could be faster, or actual access could be slower. If the access is faster, it is wasting cycles because the data is come but the instruction is not coming. However, as you are mentioning, if it is slower, then there is a penalty. That means when the actual instruction has come for execution but the data is not ready, so the execution unit will be stalled. That particular execution unit will be stalled, and that will reflect in real time loss of performance. Okay. Okay, so one other question is there was a slide on power proportional to square of frequency. If power is equal to E upon T, he has given some equation. I mean, I may not be in a position to explain that, but maybe my email address will be given at the end. Please send me an email with your query and I will answer it because it may not be possible for me to understand and you are using I think capacitance, voltage, and all those things, time and all that. So just give me explain it. My email address will be there in the last slide. Okay. So which ISA is most practical for real world application? So there is no easy answer to this. What you can say is that they have evolved over a period of time. Like uh, it started with CISC, then came RISC. Now RISC has migrated to VLIW. Each instruction in a VLIW is typically RISC. It cannot be CISC. So like this, it all depends upon the application. Like if the application is like DSP, in DSP VLIW can still be used very efficiently, but in mainstream processor, it is not possible to use them. Okay. Uh, uh, then can we use same type of instruction in VLIW instruction like add a comma b? Yes, you can do that. Yes, you can do that. So now let me just go back because we have just 10 minutes left. I will just complete this and we have about half an hour more to take the questions. So that's where I will take the questions. Okay. So moving ahead, what is the design philosophy? Okay. So VLI architecture implements two well-established concepts which were existing. It just marries the two. Horizontal microcoding. Okay. So horizontal microcoding has resulted in long instruction word. That means you have put. So now you will ask what is microcoding? It is like in the earlier processor, in CISC processors, every instruction used to result in an internal microcode, which was sequential in nature. So here they are trying to say that we are trying to make it horizontal in the sense that multiple instructions can be executed in parallel and the scheduling is decided by the compiler. So that is the first part. That's what compiler does. And superscaling processing, you already know there are multiple execution unit and that is a similarity between superscalar and VLIW. Internally they are same, but the crux is that the scheduling aspect has been taken from the issue unit to the compiler. So if you understand this, that is the basic idea that VLIW design philosophy uses. Okay. So now let us see how the actual execution takes place. This you know already. I showed this slide earlier. Now how does it change to pipelining, which has a degree of 3? So now this is an ideal situation. So now compare it with this. So what has happened is the instruction that is fetched is wide. Okay. So decode will unit will decode those 3 instruction, but it will go to the 3 execution unit. So this is one way of putting it, how the same pipeline now executes multiple. So now this is shown in a very crude manner. In reality, this 3 parallel units that you see here, that will extend to few more stages in the pipeline. Like for every execute, I mean, maybe depending on that, in some case there may be 3 writes or there could be 3 decode. That depends. This is I'm trying to portray it in a most simplest manner, saying that because the execution units are multiple, your execute cycle becomes parallel in nature. Okay, so that is a simplistic way of putting it. How the migration from superscalar to execution to VLIW takes place. In case of superscalar, there will be parallel pipelines like this inside each execution unit. So we will take an example of Itanium processor and understand how these concepts that I mentioned are actually implemented. So this was released in these are some vital statistics 2001, and this I already mentioned to you that it was a joint effort to define a new CPU architecture. So they called it explicitly parallel. That is instruction encodings tell CPU which part of the chip to be used. So I will explain that in the slides to come. And they had a very long roadmap for their family, McKinley, Madison, Deerfield, but they were never released because this is besides the point. But today what you do is AMD came out with what is called a 64-bit architecture, which is compatible with the earlier, it's an extension of Intel x86 architecture, and because of which Itanium died a premature death. However, to study VLIW, it's a good processor. Okay. So what it does is, because the memory is slow, it reads two bundles. So two instruction words are read in one shot. So what is the, I think it's not mentioned, it's 1024. Maybe it will come somewhere later. But 1024 is the width and it reads two bundles. Okay. In the extreme case, when the compiler is able to pack all the positions in the instruction word, it can execute 6 instruction per clock. Okay, so the degree of parallelism is 6. The maximum number of instructions that can be executed are 6. Remember, the execution units are 30, as I shall show you later, but the number of words in the instruction word are 6, maximum 6. So there are 30 functional units. They are in 11 groups. I will show the 11 groups later. Each unit can execute a particular subset of the instruction set. So what is a subset? Integer add, integer multiply, floating point multiply. So these are some of the subsets. And each unit executes at the rate of 1 instruction per cycle, provided the data is available. So that is the way each unit works, but the data has to be available. That is what is scheduled by the compiler. So what are those groups? So there are 6 general purpose ALU. Like the question was asked, can 2 add B comma C and add C comma D happen in parallel? Yes, they can. So there are general purpose ALUs, 2 integer unit, 1 shift unit, 4 data cache units, means they are just fetching data from the cache memory. There are 6 multimedia units. So they are useful for SIMD architecture. There are shift units. There are many times you need to shift the data. There is a multiply unit and so many of them. Floating point unit. So branch units only to decide on the branches. So total there are 30 such units. And as I mentioned, there are 6 instructions. So in a best case scenario, an instruction word will have all 6 slots populated. Okay, so this is how it looks like. So the fetch cycle will be fetching the information from instruction cache, and what is the feature from compiler that gives it a hint? Branch, saying that a branch will be taken or not. So where to fetch from? Next instruction or some other location. Issue unit, very simple. There is an explicit parallelism. It is very simple. 6 instructions it can issue simultaneously. Where will they take data from? They will take data from register handling. I don't know whether this register renaming and these things were explained in the morning, but that is handled here. Then this was also explained in the morning, bypasses and dependencies. So there is a prediction field in the instruction which predicts whether you have to bypass them or something. And this is the parallel resources like 4 integer unit, 4 MMX unit, 2 fused multiply add units, load store unit, and all these things will be, that is where the parallelism comes from. And finally, in the right stage, it will give a hint as to where to write in the memory. So what you see here is the synergy between what the compiler tells and how it is exploited by the hardware. But you won't have ideal situation always. Sometimes you have to pay a penalty if things. So always remember the golden rule. In any improvement that you do, the performance cannot be at the cannot be overlooked for accuracy. It cannot be at the expense of accuracy. Accuracy is the first important thing. Any incremental change you do, first check accuracy. In no circumstances should your accuracy be compromised. You may be delayed in some time. Like in railways, they say safety first. You should have safe operation, then you can increase the speed. Same thing here. You add a feature to give better performance, but make sure that you are never left sight on accuracy. Okay, so that is what is done here as well. And what they say is that RISC evolved from CISC. Then you in the morning you saw out of order execution and superscalar. You combine it with VLIW, you get epic. That's what Intel and HP says, that why people should go for Itanium. Unfortunately, they did not go. That's a harsh reality. Okay, So coming to the fag end, what are the implementations? Intel also had an i860, which it had VLI mode of operations. So what it would combine? It would combine an integer instruction with the floating point. And this philosophy was later used in the DSP applications. TI also make one processor which uses similar thing. And some of the other efforts are listed here. Trimedia processor which NXP came out with. Originally it was Philips which became NXP, and Shark, that's a DSP by Analog Devices. This is still in use. ST Microelectronics had ST200. TI had a series whose number I forget. So these were the processors that were available, and of course Itanium, which was not a commercial success. Okay. Now, what are the advantages and disadvantages? Advantages is that the first important thing that I have been harping on again and again is that compiler determines the dependencies to schedule the instruction. So it can do it really well because each unit, like fmac, how many cycles will it take to do the multiplication? How many cycles will it do the division? So it knows when to, if an instruction, subsequent instruction is going to use it, it will, suppose it takes 4 cycles, that instruction will come after 4 cycles. So just in time, the data is ready, the instruction arrives. There is no, see, remember when in Superscalar, when the issue unit was doing it, it had a time pressure. There is no time pressure here because instead of 1 second, suppose the compiler takes 5 seconds, that's perfectly fine because it's a one-time job. You are not doing it again. But at runtime, the time advantage is coming. Since this has been, burden has been taken off, the complexity in the hardware gets reduced. So data dependency, control dependency are not required to be checked by the issue unit. Once it becomes simple, you can have higher clock rates. Now your entire hardware has reduced. So power is reduced overall, though in some cases like data bus width is increased and because of other things, the power will be consumed there, but overall power it might get. So it's a potential. Again, it depends upon the implementation, how the designer is taking advantage of this. There are a few disadvantages, and these are some of the reasons why it did not come in mainstream. However, the concepts are extremely important, and in bits and pieces they are used today in all the practical processors that are being sold. So first thing is higher complexity for the compiler because scheduling has to be done across instructions. This is an additional burden, you can say. Then every architectural feature that you incorporate has to be exposed to the compiler. Otherwise, how will the compiler take advantage of it? So if the hardware designer makes some changes to make it fast or something, suppose he reduces the clock cycles of the floating point multiply unit, it has to be immediately told to the software, the compiler writer. In case of Superscalar, this is not required. He could had the liberty of doing any improvement without the code being changing. Then compatibility across the member, like if Deerfield comes and it has some improvements, then the compiler has to change because some changes in the hardware has to be reflected in the compiler has to know about it. Then there are some unexpected events like cache miss we already discussed, or some interrupt occurs. Then the scheduling goes for a toss. It will recover eventually, but there are such bleeps that will come in the performance. Code density. Now you cannot help, or suppose there is like in case of Itanium, all 6 slots will not be filled. So whenever there are more the number of bubbles, that leads to waste of memory space because memory is anyway 6 instruction wide, and there are some instructions are missing. That means you are wasting that space. You are fetching them also, but not using. So instruction bandwidth is also lost. And last but not the least, no human being can I won't say no human being, but it would be really take a lot of sweat if somebody tries to do an assembly language programming, efficient assembly language programming. Okay? Just for sake of running, one can definitely do it, but can't do it in a practical way. Human efforts cannot match that of compiler. Of course, the compiler is written by the humans. So to end, I missed the time target by maybe due to question by 7 minutes. Doesn't matter. Giving you all this knowledge was more important than taking little more time. So VLIW architecture, as I mentioned, Josh, he made this architecture to improve instruction level parallelism. and it tried to address the problem faced by Superscalar, because issue unit was very complex and it was under time pressure because it was doing dynamically. This dynamic time consuming task was shifted to a compiler which it could do statically, and there was no time pressure. So that was the first compelling reason. And we also saw that as far as instruction set goes, sys instruction set and RISC instruction set are biased towards software or hardware respectively, but VLIW tries to strike a balance between the two, because the DSI is midway between higher level language program and the processor. However, the complexity of the compiler and strong dependency on architectural features, any changes in the architectural feature, are the compiler is susceptible to that. And because of this, the commercial implementation did not last long. So, but there are still some of them are there for an embedded platform where the CPU itself is simple. Like DSP is a fit case because you always need a mix of integer, floating point, and their algorithms are like known, like things for video processing, audio processing, fast Fourier transforms. These algorithms you can have a good compiler translate them into for exploiting the parallelism that it offers. And that brings me to end. And this is my email address. Please note it down: ashishk@cdac.in. So some of the questions that I could not answer because of time, as well as the complexity of question, because I have to look through them, I mean understand them before answering. Please mail it to me. Now I will take up questions that you have. Sorry, I have uh, taken about 8 to 10 minutes more.
It's okay, sir. Thank you, sir, for the lecture. Yeah, so there are some questions on the chat box.
Though are there? I can't see any,
Yeah,
because
one
the
or
last
two.
question I see is which IC are used for supercomputer. Okay, there is one. Okay, so now again, I think this question you had asked Govindarajan sir also. So now actually what happens is today's supercomputers are built using you can say commodity off the shelf processors. So like you get supercomputers based on ARM, you get supercomputers based on Xeon, you get supercomputers based on PowerPC. So there, as I mentioned in the second slide, that uh, their floating point operation is the main thing. So anything that does floating point operations good, that is they will support it. And there the cores are in millions of cores are available there. So there the philosophy changes, and the ISA is same as that is used of the native processor. Like Xeon, it will be CISC, ARM, it will be RISC. So that's how it works. You can unmute and ask your questions if you so wish.
So did you get to answer the above question? Just the above? Can we use the same type of instruction?
Which type of instruction? Yeah, I made that. I said
Okay.
that there are multiple add units. I mentioned that. So if so that I have answered. While this I answered while I was taking the class. Okay. So again, the previous to that I said earlier itself that the answer is not easy. So you will have in practice you will have some combination of features from, like I mentioned, in epic computing they took something from out of order, superscalar, like this they try to compare. Okay, so I mean they try to combine and put it together.
Okay, so while in the
So I
meantime,
hope
while
it was understood. I hope because it's a slightly different concept, but anyway the recording will be available for you to see it later.
yes. In the meantime, Professor Arka, are you available? There are some questions. Last time, some students have posted.
Sir, I have one question.
Sure. So I'm posting it on the chat box.
While I think some of these questions the students already asked during the lectures, and if they have more, they can actually just unmute and ask the question.
Okay, that might be better.
Okay, sir, there are two questions that I will answer now because this is a common time for all of us through the day. So now Prithvi has asked, how does the compiler work for branches which depend on the runtime, like if then else? since the compiler will not know which instruction to schedule next. So that is where see what happens is, to give one example, it's a loop instruction that has caused a branch. Okay, so there it is very clear that the branch predict, the compiler will say that it is going to go back to the first part of the loop. So now the point here is that suppose this loop is executing for 100 times, then the loop will execute 100 times, but 101st time it will fall through. So this compiler will not know that when it is going to fall through, because 100 or 90 or 80, that is a runtime number. So what compiler by default will say is it is going to go back to the first instruction of the loop. But n minus 1 time or n times it will work, and 1 time it will be wrong. So whenever it comes out to the branch predictor comes out wrong, there is a penalty that is paid. So I hope that answers your question here. Okay. So the next question is to utilize superscalar design. Is the compiler a must? So no, the answer is no. So compilers are not aware of superscalar architecture. The compilers will simply generate sequential code. There is no parallelism inserted by the compiler for superscalar. Typical, I mean the native superscalar. If using superscalar, some advancements have been made, and there is some synergy between the compiler and a specific processor, then it may happen. So, but from the VLIW architecture perspective, this is the answer. If this question is for the second lecture of the day, then professor can answer that. Okay, and the next question, I think WR dependency is not required.
Hi, Professor Arka. You are here, right?
Yeah.
Hello.
Yeah.
I have a question, sir.
Yeah, sure.
Can there
You
be
tell
three
whom it
bit?
is for.
It is related to branch predictors. It is related to branch predictor.
Yeah, go ahead. Good.
So, sir, instead of 2-bit predictor, can we have 3-bit predictor with 8 states, which will be more accurate, or kind of thing?
And I don't know what was actually taught in the lectures that Professor Govindarajan, but in general, of course, you can actually put more state, and in general, more state you put, there is a chance that it will get actually more accurate. It's not always true, but in general, the more accurate predictor, there is always an extra state over it. Basically, what they are, these predictors are trying to remember something, seeing some pattern, and based on the patterns that they have seen in the prior, they are saying that okay, this thing will actually, history will repeat itself. So if you can remember more information about the past, which means that more state, more bits, it is likely that it will be able to predict better. Now, the whole research around branch prediction is that, of course, the state is not free. Is around without with limited state budget, how can you actually predict different kinds of patterns and predict accurately? But I think the branch prediction was covered in Professor Govindarajan's lecture, who I think cannot be here because he's in US right now.
Yes, sir. Yes, sir. I have one more question to related to software pipelining and hardware pipelining. So, sir, how software pipeline in compiler differ from hardware pipeline inside the processor? Means both are the pipeline. One is software, one is hardware. So, is there any optimization between both of them, or?
No. This is kind of an both are pipelining, but the concepts are different. There is no optimization between them as such. Hardware pipelining, as so basic idea is that you chop it into smaller pieces, the stages, and what you are trying to actually do is that when one stage is working on for say one instruction for one it is in one stage for one instruction, the other instruction can be in another stage, and it in general improves throughput. So that's the purpose but I don't see like what you mean really by, or like there is a coordination or as such.
No, I was like both chop the instructions into pieces and do in one at a time in parallel to increase the throughput. So what is the difference at hardware? I can understand that it is doing to increase performance, but at software point of view, in software pipelining, what is its use from the compiler's point of view, especially?
The basic thing is that you are trying to improve the throughput. Software at a higher level has a bigger, more semantic information, bigger windows of instruction that it can play around. In the hardware, always there is a problem of like how much state you can actually have. Deeper you actually take the pipeline, that's also fixed in the hardware, and also comes with like longer bunch penalty, and deeper you pipeline you have, so the bypass and everything gets complicated. So software, it is like that's in general the similar principle in terms of pipelining, but you don't have those hardware constraints, or that we talk about, like whenever you have something in the hardware, it is fixed for that processor at least. I also don't know how much Professor Govindarajan actually covered in terms of software pipelining, so don't.
No, there was nothing related to software pipelining. I was just asked.
Okay.
Asked.
I think the software pipelining and things might be actually covered later in the parallel discussion on the parallel processing and so on.
They were hardware pipelining, sir.
No. Later in there is a lot of lectures, right? Like there are parallel computations and so on. I can see in the schedule, so it might be covered there.
In future, it may be.
Yeah.
Yes. Thank you, sir.
I will take one question, sir, which is in the chat box. The question is, Nikunj asks, how can, let me just scrolled up. Let me just take it. How can optimization of VLIW processor be improved for large scale real time applications? Okay, so maybe I can give, maybe I may not be able to give a generic answer, but let us assume that the real-time application is working on, let's say, a streaming data, let's say a streaming video, and there is some transformations to be done, or some search in that, or something like that is to be done. And there you have an algorithm, and the data is streaming, and the algorithm is fixed on that side, that is working on them. And the basic idea of VLIW is that in one clock cycle you are able to do more than one operation. And if this can be managed, the algorithm can be managed in such a way that you are able to appropriately schedule the instructions within these the slots that you have, then this could be a fit case for use of VLIW processor to improve the performance. However, having said that, if this is not done correctly, or there could be some kind of algorithms which will definitely not benefit at all from VLIW. In fact, they may become counterproductive if the delays that the compiler expects or assumes are not same as that, or something like that. So it is like like any other technology, it's a double-edged sword. If you have it use the right edge, then you can cut it, but if you are using the wrong edge, then you end up bleeding. So that kind of thing. So I hope that answers your question, Nikunj. And then the next question, there is by Anmol. There are third one I will take in continuation, which says, are either VLIW or Superscalar power aware architecture or suitable for low power design? Okay, see, it's like this. Let me put it this way. The reason why VLIW or Superscalar came into existence was because we wanted more performance, and to achieve this more performance, more logic was used. So as a result, they are using more logic because you are the whole idea is to have more performance. And whenever you have more performance, even you take supercomputers or performance aware, I mean, where the performance is a key, there you have to sacrifice power. However, you can have certain designs, like, I mean, suppose one of the low power typical application is mobile phones, and suppose you want to have super scalar, or I mean, there are I mean, is superscalar a better suited for low power design? Then something else will be better if you are designing from scratch. But suppose you have a superscalar processor already with you, the software hardware is available, and you want to adapt it for low power design, then that's a different design philosophy or approach that you have to take. So this is what my answer for that third question would be. Then, sir, would you take 1 and 2, which are asked by Anmol?
Yeah, where are those in the? So I'm trying to actually see I can actually see one from Tarun.
No, before
What?
before Tarun.
Before that, there is from Anmol, right?
Yeah, so part 1 and 2 of that, third I have answered.
Yeah, sure. Okay, when do we refer to thread level parallelism over prefer? Okay, so did we actually teach thread level parallelism? I am not sure if we have we. I think if not, Anmol, I think you should actually hold on to these questions. A lot of time, in general, the high level answer is that, ILP is very much part of the compiled program. That is the, property of the program. So, you might not actually have even ILP to exploit for some applications. And the TLP is more useful, and it's the same thing here. Like, whether the application or you have multiple processes that can take advantage of TLP in the processor. The TLP can be in the form of simultaneous multi-threading, or you can have multi-cores and so on. But it comes down to, there is nothing about preference. It depends on, whether you have enough ILP or TLP to exploit, and both can actually be there. Like, it's not that you just can have one of it. Yeah, coexist. So the second is there any mainstream branch prediction used like 2-bit predictor? Means these days branch predictors are pretty complicated. For example, the latest, say something like AMD Ryzen or something in a Zen 3 course, they use perceptron-based predictors. They are pretty complicated. Branch predictors are very complicated. So definitely, like in some Tage predictors are actually used, but these days these perceptron-based predictors are also getting used. Okay, and there is one more about Tarun. Yeah, so it seems like, so your question about this is something that I have to check back with the slide. So what you are actually asking is that maybe why the add R2, R3 to R7 and add R6, R7 to R8, why they cannot be fetched at the same, get into the fetch at the same time, right? That is,
yes,
I
sir.
think, the question.
Actually, I could not elaborate that during the class.
Sure.
But as I was saying, according to me, I mean, this is maybe wrong in that aspect, that this would fetch a decode stage. So the add R2 and R7 can be fetched together. So in your case, add R7 and load 0 of R8. They were fetched together. So I mean, the clock cycle is same. Both are taking 10 clock cycle. I just wanted to know that what is the fault in my approach? I could not understand that.
Yeah. Let me actually see what is actually happening. So what you have is to fetch these two fetches on the cycle. So there is no more than 2 fetch on each cycle. Like, that is something that you have to actually make sure it doesn't happen. And then what would also happen in your case if add R2, that instruction is stalled? Yeah, so the problem will be this. So it is not stalling on fetch. Basically, what happens in the decode stage or RD is where you read the, you understand the what instruction fetch is just you fetch it. You don't know what that thing is, what that instruction. You don't know even the byte code in opcode what the instruction is supposed to do. Neither you really know its operands and so on, right? So when you actually stalling, you are stalling in the decode stage. Okay. Now the problem here is that your decode stage is already busy with 2 instructions. Your this add R4 would be busy, add R2 will be busy. So until there is something that is going to get into the fetch stage, like, there is no point, like, what you would actually do. So you cannot actually, so until you decode, you don't know your operand and you don't know whether you have to actually put the stalls, right? So the held up will be there, right? And if you have 2 instructions that are already in that 2 decoder, because this is 2-way assumption, 2-way superscalar. So those decoders are held up. Like those decoders are actually, you cannot have more than 2 instructions held there.
Okay. Got that, sir. Thank you so much.
So there is more questions, I guess. Okay, there is one. What is during the decode stage of various control signal generated? So in superscalar architecture, there are several instructions going to decode stage at the same time. How does the processor manages control signal generated at the same time? Which control signals? Okay, so let me read the question again. Don't fully understand. During the Shaheb, if you are there, you can actually ask the question. Unmute and ask your question directly.
Yes, sir. Am I audible?
Yes, you are.
So my question is like, in a simple processor, when in single stages, when the instructions are brought down from instruction fetch to the decode stage, it generates the control signals like read from memory or something like that. Add. I mean, write to memory or something like that. So I was just asking, like, in superscalar architecture, 2 or multiple instructions are going into the decode stage at the same time. So they will generate, of course, the control signals. So how the processor manages those control signals? I mean, which one to prioritize or something like
No.
that?
So there is no now priority like that. Basically, what would actually happen is that, so if it is a 2-way superscalar, right? So there will be 2 decoder unit. Both of them can be actually run in the same at the same time and the same cycle. So 2 separate independent instruction can be in 2 decoders that you actually have in such a, or 2 or 4, depending on what is the width of the superscalar. So there is no mixing up there.
Okay.
Does that make sense?
Yes.
Okay, so there was one more. I'm not sure if we have taken this Shweta's question. For bypassing a value, let's say from ALU output to an early stage of another instruction dependency, is it always so that ith fourth, okay, what is that, will be executed?
Instruction 4th will be executed first. I+1 and ith. Okay.
Oh, okay. I and executed first, and then I+1 in the third stage will be executed. So bypassing a value, third stage will be executed, fourth stage. So basically, what is actually happening with the bypassing here, Shweta, is that instead of waiting for the value to be written to the register and from there fetch it. So just when the result is ready, you actually bypass it to whoever actually need it. Okay, next dependent. It is not necessarily that it is just the execute stage where the result of a previous instruction will be available. It can be something like mem stage. Not only that, in a deeper pipeline, there can be multiple execute stage. And we have also seen this one example where there is a in not unified pipeline where you have different after the your fetch, decode, operand read, the pipeline diversifies and you have floating point pipeline, you have integer pipeline, and so on. They can have actually different lengths in terms of execution cycle or execution stages. So it not necessarily, it depends on what instruction that you are actually depending on previously. So from there, it will be actually routed to the input of the dependent instruction without going via the register file, because the register file write would actually happen at a later point of time, right? Like in write back. And there is no point waiting for that extra cycle, since the result that you need for your computation, the dependent instruction needs for the computation is already available. Now, when it would become available depends on the instruction you are actually depending upon, right? That's the reason you also saw that when we were talking about how the bypass network actually blows up in size, there was a term P involved there as well, not only the n square, which is the number of the width of the in a superscalar width. The P is the number of stages from which the result can possibly come. And it will depend on which instruction it is actually depending on. So it's not like fixed as such. Does it make sense? Okay. Here, anybody? Any other question? Oh, there is a. Okay. Any other question? Oh, is there, okay. I guess no other question. Then I guess we'll. Is there anything else, Vishwesh?
No. I think we are done for the day. Thank you all the speakers, and Professor Govindarajan also is not here today, for conducting the sessions and clearing all the doubts.